Hi again, everybody. Welcome back. Yes, it's time to continue playing with SN2 reactions. And let's see how many crazy and wild little PowerPoint animations I can put in. But I promise I won't use the stupid little sounds. I hate the little car. Ooh, hate that. So, but you never know when animations will come your way. Okay? So be on the lookout for weird PowerPoint animations. Okay, sorry, I digress. Let's have some fun and continue playing with SN2 reactions and looking at all four parts of the nucleophilic substitution reaction to see how could you design the best SN2 reaction ever if you wanted to make it go really fast in the rate law or make tons of product. You want to know out of all four parts of our reaction here displayed right over here, what is the best nucleophile, the best substrate electrophile, what can you create, best leaving group, best solvent. We're going to always try to get the best. So what are we going to do in this little video? We are going to focus on not the nucleophile first, which might have been what you thought, but no. We are going to pay attention to the substrate carbon today and what would make the best substrate carbon the best electrophile for an SN2 reaction. Okay? So that's what this is going to be about. So before we can start talking about that electrophilic carbon, it'd be great if we could talk about it as giving it a name. Sorry, little nomenclature here, but just to keep saying, oh, that carbon over there, that carbon over there, that thingamabob over there, doesn't really work when we're trying to speak orgo. So here comes the language of how we will talk about our electrophilic carbons. Every electrophilic carbon will have a first name and a last name. Woohoo, just like us. So there's only one Beyonce in the whole crowd, and that's the aromatics. They're a little aromatic, Beyonce-like. They only get one name. But everything else will have a first and last name. And what's even more important is if we describe a substrate electrophilic carbon and give it a name, the leaving group that's attached to it inherits that name. So we can talk about that leaving group is attached to a specific type of electrophilic carbon and therefore behaves like a leaving group attached to that carbon. So it's like a family. Okay, so let's start off with looking at the first names. What's the first name and what's the first thing you want to look for in any carbon? So any of these could have a leaving group attached to them, none of them do. But if they did, then we could talk about them with a first name that goes as follows. It's pretty straightforward. If this carbon only has one other carbon attached to it, it is called a primary carbon. What do you think a carbon that has only two other carbons attached to it is called? You guessed it, secondary carbon. And tertiary carbon and quaternary carbon. And we can label these things by using these abbreviations: primary, secondary, tertiary, and quaternary with little degree symbols by them. Not sure why they use degree symbols. This must be old-fashioned terminology. So this is how every single electrophilic carbon will be one of these four possibilities: primary, secondary, tertiary, and quaternary. Unless it's aromatic, then it's Beyonce-like, just aromatic. All right, so here's the first name. What are the last names they could have? Well, if I'm a leaving group attached to this carbon here, then I only get one name, aromatic. Got to come up with a cooler sound for aromatic. Okay, but if I am a carbon that is not attached, so let's look at these familiar. Let's come at it the other way. Aromatic's the coolest. So let's look at almost cool. Almost cool is a carbon that's almost on an aromatic ring. It's almost on benzene. Therefore, we give this carbon that's almost on benzene, one away, the name benzylic. That's its last name. So this happens to be first and last, as you can see. You can see that it's attached to 3 different carbons. It's a carbon almost attached to the aromatic benzene ring, and so we call it benzylic. It is different from, say, a carbon that is involved in just a double bond. These are called vinylic, and they can have primary and secondary vinylics. We won't spend much time with those, as you'll see in a minute. But the ones that we're really interested in are things like these allylics, benzylics. These will play a big role in our nucleophilic substitution experiment reactions. So we want to be able to spy these. And notice allylic is almost vinylic. It is attached to a double bond. But if it was attached to a benzene ring, it's not allylic, it becomes benzylic. You can see all these little family names. Yeah, they're slightly different. But they have very dramatically different chemistry associated with them, which is why we need to give them these last names, similar to our functional groups. Drastically different chemistry, drastically different names. And therefore, the catch-all, end-all is if it's not aromatic, if it's not benzylic, if it's not vinylic, if it's not allylic, if it's none of those specialty names, then we group it all into the generic catch-all name for anything that's not one of the other 4, aliphatic. So these are typical you can see this carbon's an sp3 carbon, nothing fancy. It's not attached to a carbon with a double bond on it anywhere, so it's not allylic, it's not benzylic. So this is just known as an aliphatic. And since it's only attached to a primary carbon, it's a primary aliphatic. Okay, so those are really, really important to grab. Put them on Post-it notes. Again, add them to your lexicon of Orgoland terminology that you and I will be able to discuss, and that I could put a leaving group on any of these different types of carbons, and therefore just say, oh, looking at that structure, what would happen if I put a leaving group on that aromatic carbon? Or what would happen if I put it on that primary allylic? And you'll know exactly which carbon I'm talking about. That's the key to this nomenclature, that we can speak to each other in Orgo. Yes, so cool. And that other people will have to charge us thousands of dollars to translate their organic chemistry terminology for them. Yeah, okay, like any good foreign language. Now that we know that terminology for the substrate / electrophile, electrophilic carbon, let's dive deep into what makes a good substrate / electrophile for SN2, and only SN2. I want to be really clear, this entire conversation is all about that experiment number 2 reaction mechanism, SN2, with the British guy's voice. Okay, so when we're looking at that, remember this whole mechanism required it to happen in 2 steps. That as the OH minus approaches from the backside of the leaving group, the transition state is some combination of all these in one place around this electrophilic carbon. And so if I'm going to have the nucleophile come in from the backside, it'd be nice if there wasn't a lot of steric bulk in the way. So as you can see, this is a primary aliphatic carbon versus our secondary aliphatic versus our tertiary aliphatic. And you can see the pattern here is the more bulkiness I put around the electrophilic carbon, I essentially go to a place where no reaction occurs at all, or so slow that it's nothing you would ever want to design. That tertiary aliphatics, I hate it because they're so bulky in the back with all these methyl groups here, huge steric hindrance here, that this OH can never find that electrophilic carbon from the backside. And remember, it's not going to attack from the front side because that bromide is already partially negative. So if in our world it really is this mantra forever, I will never have the OH minus coming in where the Br minus is. So, and it's not a full minus, it's just a partial minus due to this dipole. So that'll never happen. So this backside attack works best on primary carbons. Okay? So now we have a way to build different electrophilic carbons and have them react differently in SN2 reactions. So the best substrate on this theme again, let's think about these other guys. What if I had primary everything? So even though I have the first names are primary, are they all the same? And what would be the best? So notice when we did an experiment with primary aliphatics and primary allylic and primary benzylic leaving groups, they did not all react the same. That this primary benzylic is awesome, but the primary, aliphatic is good, and you can see not so bad being primary allylic. So just being on a primary is great, but why does being on a benzylic or allylic carbon cause it to react 40 to 120 times faster? This is a touchy subject. So let's take a quick look, and please ask me questions about this, because this slide might not do it justice. I try. So here, if I were to ask you what kind of, there's our leaving group, what kind of carbon is the leaving group attached to? What's its first and last name? You would want to say how many carbons is it attached to? Ignore the leaving group. So you would see that it is attached to a primary, only one other carbon, and it's primary. And which kind of last name would you give it? That primary carbon has a double bond next to it. That looks like this type of structure here. That's our friend the allylic. So this is a primary allylic. So we want to take a close look. As you can see from this slide over here, we can see, and all of a sudden I want you to get attention to the double bond that's actually next to the transition state. So as the nucleophile comes in and we form this transition state, where both the leaving group and the nucleophile are trying to come in and leave, the electrophilic carbon starts feeling a little positive. That's a little uncomfortable. Anything I can do to make that positive smaller by resonance, can't do resonance because this isn't a full positive charge. It's just a partial positive. So anything I can do. Well, if you look in those drawings, notice I do have a pi bond right next to it, full of electron density, a pair of electrons sitting in this p orbital. And so what it can do is it can maybe just through space, this partially positive carbon is looking up and goes, wow, there's a pi bond right next to me full of electron density. Woohoo! Oh, if I could only, wait, I got too many bonds. I can't do resonance with it. But maybe I can just sort of reach up and enjoy those electrons a little bit. Pull them down a little bit towards me. Please help me is what the carbon's saying. And it does. It doesn't create a resonance structure. It doesn't create anything different. As you can see, all it does is improve this reaction by making that little carbon's partial positive smaller. Did you see that? Now it's a little red, partial positive. Wait, it took me so long to make that happen. I gotta show it to you again. And the actual electrons, that little p orbital feels like it's got some electron density in it, and it doesn't feel as largely partially positive. So this will increase this transition state, make it happen easier, faster, and get to our final product. This entire process of just reaching up from a pi bond next to me and pulling electron density towards me, but not by resonance, is called hyperconjugation. Big fancy name. So it's like an electron donating group because I can't do resonance with it, but you put these pi bonds near electrophilic carbons who are partially positive, and you make their partial positive smaller in the transition state, that reaction will happen much faster. And so notice I have the same kind of drawing in the same environment for my primary benzylic. The leaving group is attached to a carbon next to a carbon with a double bond, so I can get hyperconjugation with benzylics. And there's so much pi electron density in the benzylic, in the aromatic ring, that it has even more ability to, take some of my electrons. I got tons in the ring, don't worry, I got tons in my ring up there. So have tons, and this is what makes it even react even better. So if you want to make the fastest, most product in an SN2 reaction, put your leaving group on a primary, less sterically hindered primary benzylic carbon, and woof, look out, explosion. It might happen so fast that you're out of lab in like 5 minutes. So we love designing experiments that are on primary benzylics. Okay, how's that feel? A lot of new terminology. Still, it's plus loves minus. So what will I never put a leaving group on? What will I never have do backside attack in terms of a nucleophilic substitution? And I'm even taking out the SN2. I mean any nucleophilic substitution reaction now as an electrophilic carbon. What would I never want to put a leaving group on? And now you can see, I never want to put it on a carbon that has a pi bond. Look at all these beautiful renditions of all this electron density. Can you even imagine trying to get a nucleophile to do a backside attack through this pi bond to get to that carbon? Never, 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 never. Okay, did I say never enough? Really? Never. So make sure that if you ever see a vanillic halide or vanillic leaving group or aromatic leaving group, like this bromide on a benzene ring, these are awful and they will never react in a nucleophilic substitution reaction. It doesn't mean they never react. Wait till you take Chem 212, great course. In that course, you will learn experiments that react with these species, but they're just not nucleophilic substitution reactions. Cool. So let's put all our substrate knowledge to good use. Here's a multiple choice question where I've given you all possible nucleophilic substitution reactions. And I've given you all the same nucleophile, all the same solvent, heating them all the same, all the same leaving group of some kind or another. Don't even want to worry about that. But notice the leaving groups are attached to various carbons, and those various electrophilic carbons have first and last names. And try to go through and rank them from which one would be the best to which one would be the worst, and maybe none of these fit any of the rankings in the order that I've given you. What would be also cool is please start practicing, show the products. What's made in these reactions? Because there is a reaction taking place here. And if we get used to not just trying to kind of see substrate, electrophile, nucleophile, but keep in the back of my mind that this is all trying to help us make these cool functional groups, that's a really nice tying it all together and that you're making these cool functional groups. Okay, so try this one for class. And let's see. I got another one for you to play with for class. So these are great. You guys have been doing a great job in your new study groups. Please, again, try to come to the study groups with possible answers for these. I don't care if they're horribly wrong, but at least it allows us to have a discourse about what were you missing, what were you not getting out of this lecture, because it's very hard to learn organic chemistry. I don't know how you guys are doing it by watching me on video. Oh, so sorry. But we'll try to make it entertaining as best I can, and hopefully you'll be back again to see lecture 13 for tomorrow's class. Okay? All right. If you have any questions, please let me know. As you know, I love questions. Okay. See you guys later. Bye.